So what's biomimicry? The combination of human ingenuity and the amazing kind of array of evolved adaptations in nature. That's an incredibly fertile combination. Sometimes biomimicry can lead to an interesting combination of kind of medium to high-tech equipment together with very low-tech material. What we should be doing when we're designing a new building or a new piece of city is we should start by analyzing how does a mature ecosystem in that part of the world function? How much carbon does it sequester? How much water does it filter? How much oxygen does it produce? How much food does it produce? How much wildlife does it accommodate? And those should become the targets for our new piece of city. So the short version of what I'm going to say is that conventional sustainability is not enough. We need to go beyond that into the realms of regenerative design. And I'm also going to be making the case that the solution to our nature crisis can be found in nature itself, in the myriad adaptations that have evolved on planet Earth. And I think this challenge of the planetary emergency is going to require us to rethink what it means to be human. So before I get into all that, I just want to say a few words about this slide. It's often said that the first photograph taken of planet Earth, the so-called Earthrise photo, that was what kick-started the environmental movement in the 1970s. In many ways, I find this a more compelling image. So this was taken by the Cassini spacecraft. As it was passing Jupiter, it turned around and it took this photograph of planet Earth, this little pale blue dot in the vastness of space. And when I look at that image, I think it's clear from that that no one is coming to our rescue. You know, whatever happens is up to us. It also makes me think about our place in the cosmos and our place in deep time. And there's a science writer called Janine Benyus. She has a very good way of conveying this idea of deep time. She encourages people to imagine the history of planet Earth as if it were represented as a single calendar year. And imagine you're at midnight on New Year's Eve, and you're looking back over the course of that year. What you'd find is that the first life forms appeared in March. It took all the way until August for that to evolve into multicellular life forms. In mid-November, the Cambrian explosion resulted in a massive expansion of biodiversity. The dinosaurs emerged in early December. They disappeared on Boxing Day, the day after Christmas. The first hominids arrived at 8 p.m. today, the 31st of December. The whole of recorded history has flashed past in the last 30 seconds. In the last 2 seconds, we became a geophysical force affecting our whole climate, emitting 500 billion tons of CO2 into the atmosphere. In the last third of a second, that's the time I've been alive, we've extinguished more than 2/3 of the wild animal biomass on planet Earth. So from this perspective, it would be easy to conclude that we are racing towards extinction. I don't think it's quite as bad as that, but if we carry on as we are, we're heading in a very dangerous direction. And what we do in the next fraction of a second in this analogy is going to affect the whole history of planet Earth. Now, there are a lot of powerful people who would like you to believe that we don't really need to worry, the current economic system is fine, and technology has all the answers. I don't think that's true. I think that's quite a dangerous course of action. I think technology has some of the answers, but more importantly, we actually need profound cultural shifts, particularly in how we see ourselves and our relationship with nature. This image here, this comes from a book called The Good Ancestor by Roman Krasnarek, and he suggests that there are 3 possible pathways for humanity. So one is the breakdown pathway, the other is the transformation pathway, and the third one, that's the kind of worrying, slippery one, the reform pathway. That's the pathway in which enough governments and enough big businesses persuade us that action is being taken that is enough to address the planetary emergency, when in reality, that is not enough. It doesn't meet the magnitude of the challenge. And that is very much the pathway that I would argue nearly all countries are on. I'm not going to say much more about the sort of gloomy side of things, and most of what I'm going to be talking about is how we get on that transformation pathway to charting a safe course for humanity. And a big part of this is shifting beyond conventional sustainable design. I think this diagram from Bill Reed helps to get across the key differences between sustainability, and regenerative design. So this shows different levels of environmentally responsible design, starting with conventional practice. Above that is the realm of green design, and I'm sure you've heard of rating systems like LEED and so on. And then above that is fully sustainable, which the architect Bill McDonough has characterized as being 100% less bad. Now, I've been working in sustainability for nearly 30 years, and I thought all that time I was making things better. And so it was quite painful to realize that a lot of what I was doing was just making things a bit less bad. And until we get above that line of neutrality, we're just part of a degenerative system. So the challenge, really, is how we get above that line of neutrality into the realms of actually having a net positive impact. And just as we had very lively debates about what the ultimate in sustainability meant, now I think we need to be having an equally spirited discussion about what the ultimate in regenerative design means. And for me, I think it is about getting to the point where we've overcome our separation from nature and we are actually participating and co-evolving as nature. I'll say a bit more about that in the course of the next 40 minutes or so. So for me, there are three big differences between sustainability and regenerative design. One I've mentioned, the difference between less bad and optimizing positives. Another is that sustainability tended to be just about humans. It was very anthropocentric. And we need to expand that to include the whole web of life. And the third is that conventional sustainability tended to be rather mechanistic. It would just focus on a limited number of metrics like carbon. And we need to expand that as well to a much more systemic, much more holistic approach. So this is one example of the kind of thing that can get missed if we focus too much on carbon. Obviously, carbon is important because climate change is one of the most worrying trends. But if we just talk about carbon, we risk missing some other important things. I wonder if anyone is willing to have a go at guessing what this is showing. So these are three independent studies. The dashed red line is the average projection, and the dotted red line is a critical threshold. Anyone willing to have a guess what this is? No? No, you're all shy. Well, this is what's happening to the European male sperm count. And the dashed line is regarded as the threshold of fertility. And I find it amazing that there isn't more discussion about this. I have written to multiple health ministers about this and never get a satisfactory response. A lot of this is to do with the way we make things. We use rather sloppy chemistry. We emit a lot of pollutants, particularly endocrine disruptors. And bear in mind, this is going to be affecting a lot of other animal species as well. Excuse me. Now, this example makes the point about needing to look at the whole system. Let's just say you wanted to create clean electricity and you built a dam across a river. You could argue that once that clean electricity has paid back the embodied carbon in the dam, then everything you get from that point onwards is zero carbon electricity. But it's not quite as simple as that, because we know from scientific studies in North America that a lot of the nitrogen in the forests there would have come from the oceans via vast flows of salmon swimming up rivers where they get eaten by bears and eagles, and then that gets pooped out into the forest and the nitrogen gets taken up by the trees. So when you build a dam across that river, you also block the flow of nitrogen, and then the forest becomes fragile and more susceptible to forest fires. And when that happens, that's a carbon nightmare. So if we just look at carbon, we risk making an even bigger mistake. And this example conveys the importance of understanding complex systems. In the 1960s, the World Health Organization wanted to do something about malaria rates in Borneo. So they sprayed a lot of DDT around, which killed the mosquitoes, and the malaria rates went down. So far, so good. It looked like a success. But what happened next was this expanding wave of unintended consequences. Because the DDT also killed the wasps, which were predating on the thatch-eating weevils. So without the wasps, the weevils ran amok, munching their way through everyone's straw roofs. The roofs collapsed. The World Health Organization felt responsible. So they paid for those roofs to be replaced with metal roofs. And those drove everyone nuts in the rainy season with the noise, and they kind of roasted in the hot season. And then things carried on getting dramatically worse because the DDT bioaccumulated up the food chain. The insects were being eaten by geckos, the geckos were eaten by cats, and the level of DDT in the cats was so high that all the cats died. And then the rat population went absolutely exponential. And fearing an outbreak of bubonic plague, the World Health Organization mounted what is surely the most bizarre operation in its history. It was called Operation Cat Drop, which involved parachuting large numbers of live cats into Borneo. I swear this is a true story. I wasn't able to find an image of parachuting cats. So this shows what can happen if you intervene in complex systems without really understanding complexity. I'm equally convinced that if we get better at dealing with complexity, we can learn to intervene in complex systems to deliver multiplying benefits. So what I'm going to talk about now is how we can use biologically inspired design approaches to help address many of these issues. And for me, biomimicry is distinct from biomorphic design. So biomorphic design, and this is one example, is about copying nature's forms for, say, poetic effect, in terms of meaning and so on. And it can produce some majestic architecture like the TWA terminal by Eero Saarinen, but this is not biomimicry. Biomimicry is a functional discipline. It's also distinct from biophilic design. So biophilic design is based on the idea that because humans evolved in direct contact with nature, there's a lot of evidence to suggest that we are happier, healthier, and more productive if we're in regular contact with nature. All right, so what's biomimicry? Well, sometimes when I talk about biomimicry, people say, well, you know, nature's all right, but you don't get jet engines or high-speed rotating axles in nature. But if you actually look in detail at what goes on in nature, you can often find quite amazing adaptations to equivalent challenges. This is how nature has evolved a solution to a rotating axle. It's quite difficult to make living tissue continually rotate. So this insect is called a wood wasp, and it has this body part here which is able to drill into wood. And that drill bit is made in two semicircular halves, and those move in a kind of reciprocating action like that. So it can put the drill bit into a crack in the wood, and then it can pull on one side and slightly push on the other, and with no net pushing force, it can drill into wood. This has inspired a new type of medical drill bit, exactly the same approach, two semicircular halves, so it can be used in very delicate surgery, like drilling into a skull with no pushing force. And because it's in two semicircular halves, it can actually follow a curved path. So you can see from that the combination of human ingenuity and the amazing kind of array of evolved adaptations in nature, that's an incredibly fertile combination. And this is another example of a pretty amazing adaptation. So this is called a bark beetle. And a bark beetle can detect a forest fire at roughly 5 kilometers. That's about 1,000 times the distance of a human-made fire detector. You might wonder why it flies towards a forest fire. It actually flies to where the fire has just passed through, and it lays its eggs in freshly burnt wood, and the advantage there is that there are no predators around. And if you compare this to our fire detectors need a continuous piece of copper all the way back to a power station burning fossil fuels. This just needs a few nibbles on a leaf and a few droplets of water to do something much more sophisticated. Now, this is a fantastic experiment that was conducted in Hokkaido University in Japan. The scientists used a map of the Tokyo region, and they did this experiment with what's called a slime mold. So they put a piece of food on each of the cities surrounding Tokyo on the map. Those are the white dots. And then they put the slime mold on Tokyo itself. The slime mold spread out quickly, located all those sources of food, and optimized the connections between them. When it had finished, that layout exactly matched the railway network in that part of Japan. But whereas it had taken the engineers thousands of hours to arrive at that optimization, the slime mold, the single-celled organism, did it in just 26 hours. So the overall point here is that we could look at nature as being like the most amazing design sourcebook in which every product has benefited from a 3.8 billion year research and development period. And all of those represent evolutionary success stories that are brilliantly adapted to their current location. And in my latest book, I was very much inspired by a philosopher called Freya Matthews, who sets out really quite a stretching idea of what biomimicry could do. She puts forward a kind of much deeper approach to biomimicry. So she refers to a book called Cradle to Cradle, which I'm sure many of you are familiar with, by McDonough and Braungart. In that book, the authors suggest that if you imagine you were the manufacturer of a hair gel, what you should do is you should think about the river that hair gel will end up in. And you should ask yourself, what does the river want from the hair gel? Freya Matthews, the philosopher, she suggests that's along the right lines, but it doesn't go far enough. What we should be asking is, what does nature want us to desire in the first place? And that is a pretty challenging provocation, I suggest. It would make us rethink a lot of the things that we take for granted in the built environment. So I'm going to just very briefly say a little bit about what biomimicry means applied to materials and structure, and I'm going to focus most of my talk on water and thermoregulation, because those are both very relevant to the topic of heat and how we can stay cool in a hotter environment. This image here, this is the spinneret glands on a spider. Now, the closest thing that we have to spider silk is called aramid fiber. To make aramid fiber, what you have to do is you take petroleum, you boil it in sulfuric acid at high temperatures, you use extremes of pressure to get the molecules into place. Out of that, you get your fiber, and you get masses of toxic waste. So extremes of temperature, extremes of pressure, loads of pollution, and all that to do the same as a spider does with raw materials of dead flies and water. It suggests that we've got a bit to learn about how we use materials. And I actually think that we need to go back to first principles on materials and learn from the fact that 96% of all living matter is made from just 4 elements of the periodic table: carbon, hydrogen, oxygen, and nitrogen. Of the remaining 4%, that's nearly all a further 7 elements. So you can see that nature uses a very limited and safe subset of the periodic table and has evolved to create materials with much higher performance to most of ours. And here are 2 examples of how nature has evolved higher performance. So one of these is called hierarchy, and the best way to describe that is it's the idea of structures within structures within structures. So if you think of, say, the Eiffel Tower, that has trusses within trusses within trusses. So that's 3 levels of hierarchy. Most of our buildings and structures have 1 or no levels of hierarchy. The carapace of a lobster, that has 7 levels of hierarchy. And at every level, you get increased performance enhancement. The image on the right, that one is about interfaces. So that's a magnified image of abalone shell. And it's made of these layers of calcium carbonate. And those are connected together with an interface of flexible protein. And that gives it amazing resistance to crack propagation. At a chemical level, it's almost identical to ordinary blackboard chalk, but because of those interfaces, it achieves 3,000 times the toughness. And in my office, we designed a house based on this idea. So it uses curves to create a stiff shape, and then it uses layers of tiles very similar to the abalone shell. And we're pretty confident that this would use less than half the amount of material of a conventional house. Sometimes biomimicry can lead to an interesting combination of kind of medium to high-tech equipment together with very low-tech material. This is a way of 3D printing with mud. And I would argue that this is actually getting very close to the way that nature builds. Nature doesn't put a lot of energy into transporting materials over vast distances. It just brings evolved ingenuity to the site and does amazing things with the materials that exist on the site. I think we're going to see a huge increase in the use of biomaterials. This is one good example. So this is a type of high-performance insulation made from plant waste and mycelium. It's high-performance, fireproof, completely non-toxic. At the end of its life, you can literally put it into the compost, and it'll be reabsorbed into nature. Touching quickly on structures, this diagram here, this shows a bit more about hierarchy and shape optimization. So let's imagine you've got a strut here, and it's being compressed at the ends. And let's say that's a square section, solid strut, and that's 100%. You can make one just as strong that is circular with 82% of the material. There's a big jump when you make that hollow that comes down to 20%. And then you could taper those ends, you're down to 14%. Then you could introduce a level of hierarchy, and you're down to 5%. Then you could introduce another level of hierarchy by turning each of those sub-elements into a structure itself, and now you're down to 2%. And in principle, you could keep going. So this is how we could use ideas from nature to use materials far more efficiently, using a fraction of the amount of material to achieve the same results. This is a table that we designed for an exhibition, and there's nothing accidental about that shape. It's not just a wacky biological shape. It's based on bone and tree growth patterns. And what we're trying to do there is to get as close as possible to a theoretically perfect structure. And this is where 3D printing can be a real breakthrough technology. I think within a conventional sustainability mindset, 3D printing could be a problem. It could result in masses of short-life consumer rubbish. But within a regenerative mindset, it could be transformative, because it could allow us to use exactly the right materials to put those together in incredibly efficient ways, and in ways that allow near-perfect circularity. So that's also 3D printed from a biologically derived polymer. So it's taking carbon out of the atmosphere and putting it into a structure. We heard a lot about bamboo yesterday, and this is a structure by the engineer, the same engineer who worked on some of the bamboo school projects, Neil Thomas at Atelier 1. And they're using strips of bamboo glued back together. It's called engineered bamboo, and it's incredibly strong. And what they're doing here is they're getting those strips to exactly follow the lines of force, which is what nature would do. And it can result in really quite elegant and incredibly efficient forms. In my office, we've been exploring various ways of growing buildings or making buildings from atmospheric carbon. So using biomaterials and timber is one way of doing that. This is a way of growing a structure in seawater. So if you put a lightweight steel frame in seawater and pass a very low electric current through it, perfectly safe for wildlife, you get minerals building up on that structure, and it can become as strong as reinforced concrete. So we've designed a pavilion which is intended to be a performance space, and the idea is that this will be fully grown in seawater, and then we'll float it to the surface, we'll put it on a barge, and we'll moor it in a river in a big city. All right, so now I'm going to move on to water and then thermoregulation. Some of the most amazing adaptations for water can be found where water is scarcest. So in deserts, you find organisms like this. This is the thorny devil. Now, the thorny devil can drink with its feet. If it's standing on damp ground, the water tracks up grooves in its skin all the way up to its mouth, and then it licks its lips and looks rather pleased with itself. The prickly pear cactus, those clusters of spines are doing a pretty amazing job. Each spine has a very particular geometry that exploits two different pressure phenomena to essentially suck water out of the air, and even against gravity, to suck those along the spines up into the body of the cactus. It's sometimes said that camels are a horse designed by committee, and I think that's incredibly disrespectful, actually. Camels are an amazingly well-adapted species, and in a few minutes I'm going to be saying something about their nostrils. They've got the most amazing water recovery adaptations in their nostrils, which I've worked with a team to develop into a project. I dare say some of you have heard of this approach. This is called sponge cities. And this is a way of trying to get cities to come close to matching the performance of real ecosystems. And this is partly related to an idea from Biomimicry 3.8. What they suggest is that our current approach to designing buildings and cities doesn't go anywhere near far enough. Systems, rating systems like LEED and BREEAM, they're just not going far enough. What we should be doing when we're designing a new building or a new piece of city is we should start by analyzing how does a mature ecosystem in that part of the world function? How much carbon does it sequester? How much water does it filter? How much oxygen does it produce? How much food does it produce? How much wildlife does it accommodate? And those should become the targets for our new piece of city. We're a long way from that at the moment, but there are sufficient examples of projects that do bits of that for me to be convinced that that is possible. And when we get to that point, we could reasonably argue that we have integrated our new piece of city into a broader, stable system. Really addressing what I think is one of the biggest challenges for humanity, which is to learn to integrate everything we do into the web of life. Before I came here, I spent a bit of time traveling around India, went to Chandigarh, and although Le Corbusier was a brilliant architect, I think his urban planning was the weakest aspect of his oeuvre. And so you see these vast expanses of hard surfaces, which I think are really about sort of aggrandizing the buildings. And it's interesting to see that many of the people that worked with him, like Balkrishna Doshi, actually moved on to a much more humane approach that uses planting to create shading and evaporative cooling. And in that sense, getting closer to what I was talking about, of matching the performance of an ecosystem. So this is a project that I worked on with a client in Nagpur. It's a zero-waste textiles factory. And as I'm sure you know, textiles as an industry uses vast quantities of energy and water. Our client wanted a zero-carbon, zero-waste factory. And to do this, we looked at the characteristics of ecological systems. So this is from my book, and it contrasts conventional human-made systems with ecological systems. So ours tend to involve mostly linear flows, whereas nature is zero waste with closed-loop flows of resources. Ours tend to be disconnected and monofunctional. Nature is densely interconnected and symbiotic. I won't go through all those, but all of the ones on the right-hand list, I think that is a very good summary of how we need to be rethinking our cities and industries to work towards the characteristics of ecological systems. And we did some of that on the zero-waste textiles factory. We conceived of it as having three main realms. There's the factory itself, and then there's the water cycle and the energy cycle. So within the factory, there are lots of different processes that are going on, each of which has its own resource flows. The big change came when we shifted the fossil fuel energy system to a biomass combined heat and power plant, because that meant we were getting electricity as well as heat for the various processes. We could make use of lots of waste heat from the factory. And then we worked with a chemist, a biologist, and a water expert to design out all the toxic elements that normally go into the textile process. And that meant that we could then use biological forms of water treatment. This is the one we used. It's called Biomatrix, and it uses plants and microorganisms to treat all the waste from industrial processes, if you can take out the toxins, that is. And we deliberately put that water treatment down the middle, and we proposed large windows in the factory so that at every part of the factory you can get a view out to nature. So we're getting the biophilic benefits from that water treatment as well. A few years back, we were asked to join a tender for a new water treatment facility in the Middle East. This is one of the company's existing plants. And when I looked at that, I thought, well, that doesn't look very efficient to me. You know, it's very rectilinear. There's a lot of space between the elements. And I wondered if we could learn something from how water is conducted in nature. So this shows a phenomenon that is referred to as Murray's law. So there's a very constant mathematical ratio between the diameters of vessels in branching systems. There's also a very constant angle at which that branching occurs, and there's a certain finessing to those junctions. that's an evolved minimum energy way of getting water or gases around an organism. And in my office, we developed a little digital tool based on this. So this is a hypothetical layout. The white circles are bits of equipment, and then there's pipework that connects them. And this digital design tool is based on Murray's law. So it's optimizing the relative positioning and the branching angle. And if you look at the total length of the pipework in the bottom left-hand corner there, you can see that we came down from 100 to below 65. And then we went a step further, and this is a very realistic layout for a water treatment facility, so all the right elements in the right sequence. And this time we combined the figures for length and angle to produce a figure for total equivalent length. So when you put a 90-degree or a 45-degree bend into a system, it's quite well known what that adds in terms of friction, and you can express that as equivalent length. So that bottom figure there, that's a very good measure of the overall amount of friction in the system. And you can see that we came down from 100 to well below 40% there by learning from nature. Moving on now more specifically to thermoregulation, termites have some pretty amazing tricks. They've evolved ways of existing in quite extreme temperatures. And you may well be familiar with this building that was built in Harare. It's called the Eastgate Center. It's pretty close to the equator. It's managed to maintain comfortable conditions without any air conditioning at all. And most of that was inspired by termite mounds. So taking benefits of the thermal mass and flows of air during the cooler times of the day. What would be really interesting is to apply some of the latest science of termite mounds into a next version of that building, because the research has actually shown some pretty remarkable adaptations. I'm going to get a little bit geeky now, because this is a part of a termite mound where the gas exchange occurs. So it's a kind of hole in the side of the mound, and it's called an egress complex. And around the mound, you get wind flows, which result in sort of oscillating wind pressures on the surface. And within the egress complex, what that does is it moves the air in and out of these places here. And at the places where it's number 3, you get mixing of gases. Now, the reason this is so clever is because it's an advantage for the termite not to lose any of the coolth or humidity within the termite mound. But because it's got a lot of living organisms within that, all taking in oxygen and giving out CO2, it needs to exchange, it needs fresh air, basically. So this is a way of getting fresh air, but without losing any of that cool energy. I'd love to do an actual building based on this idea. We can learn from nature to develop ingenious ways of providing solar shading. You can find lots of examples of elegant folding patterns. So the one on the left is a convolvulus flower. That one is a hornbeam leaf. And both of these go from a very compact form to a very spread out form very easily. And that would be an advantage for sun shading systems like this one, say, where you can very quickly shade an urban space. But at night, you could put that away and allow some of that heat to escape to the night sky. Some engineers and scientists in Germany developed an ingenious shading system based on the Strelitzia flower. So this part of the flower, when the bird that pollinates it lands on that, it bends slightly and it changes the geometry. So those parts of the petal flatten like that. And these engineers turn that into a shading system called Flechtofin, which they applied to this building. So most of the ways in which we provide cooling in buildings is by creating air movement like this or cooling the air within the building. And in some ways, it's surprising that we don't make more use of conductive heat transfer, because that's one of the most efficient ways of exchanging heat. And you can see examples of this in animals, ground-burrowing animals, iguanas, and so on. When they need to heat up in the day, they can bask on a warm rock. or even lie on a cool rock if they're overheating. What would this mean for a building? Well, it could mean that it's time to explore the idea of cooled seats. I know that might sound wacky, but that idea has been used in luxury cars for a long time, and that would be much more efficient than trying to cool all the air inside a building. And it's quite possible that we could achieve comfortable conditions with a fraction of the energy. We've heard quite a lot about approaches to passive cooling through thermal mass. And this is a way of adding a degree of control to that. So this is called decoupled thermal mass. And the idea here is that you have all the thermal mass in the basement here, and when you need cooling, you draw air through that, and you can provide cooling in a more controlled way. So this building was actually for plants from alpine regions, and they needed a way to keep those plants cool in the heat of summer. Elephants have very wrinkly skin, and that's not accidental. That actually helps them with cooling. I'm sure you've seen elephants spray water over themselves. With these deep wrinkles, they're able to retain a lot of that water in the cracks, and that enhances the degree of evaporative cooling. This is another interesting approach to cooling a building. This is in Japan by Nikon Seikei, and they designed these porous terracotta tubes on the facade of the building, and they use captured rainwater to evaporate moisture from those surfaces and provide a kind of cool microclimate around the building. This is an example of radiating heat. So there surely must be easier places to live than the edge of an active volcano. But this insect, the longhorn beetle, has found a way of making a go of it, which is pretty impressive. And the way it does that is it uses what is called passive radiative cooling. It's able to radiate heat out to outer space, even during the day. And there are now surfaces that you can find, and I'll show you an example in a minute, that use this idea of passive radiative cooling. The ancient Persians knew about this. They found a way to make ice in the desert thousands of years ago. And I've got a sketch animation in a minute that I will show to explain this. And a few years back, we were approached by a client in the Middle East, and he wanted us to design a building with the brief was very open, essentially. He just asked us to do something clever with water and cooling. And so we were interested in this idea of Persian ice making, and we wondered if there might be some other ideas from nature that we could use. And to let you into a secret, we were very short of work at the time, and so we really wanted to win this pitch. And we did quite a lot more research than we would normally into who was going to be the kind of decider, who was going to be deciding who won the pitch. And it turned out that the ultimate decision maker was this sheikh who was passionate about camel racing. And we thought, all right, well, maybe if we can design a building based on camels' nostrils, that would get us in with a good chance. All right, so I'll explain how camels' nostrils work now. If you were to make a sort of slice through its nose, you'd find that it has these very intricate passageways, which are called nasal turbinates. And the way those work is that when the camel breathes in the hot, dry desert air, that air passes these surfaces, which have a lot of blood vessels in them. So those evaporate moisture into the air, which means that it's cooled and humidified and is less of a shock to the system. When it breathes out, that warm, humid air passes those same surfaces, which are cool because of evaporation, and a lot of that moisture recondenses and is recaptured by the camel. The small amount of moisture that it loses, it gets evaporative cooling benefits from that, so it can keep its eyeballs and its brain as much as 6 degrees C cooler than the rest of its body. All right, now I'll explain the Persian ice making. All right, so let's just look at some comparative temperatures. Let's say the temperature of the desert at night is, let's say it's about 30 degrees C, which is quite cozy. The temperature of outer space is minus 273 degrees C, which is a bit chilly. And what you can do is you can get a a black surface to radiate heat to outer space. And that's what the Persians did. They would put a shallow ceramic tray on a bed of straw for insulation. The ceramic would have a black glaze on it. They'd put a thin layer of water on that, and on a clear night, that radiative effect to outer space was enough to turn that water into ice. And they would scoop it up before sunrise and store it and to make drinks and impress their friends with. So how do we turn this into a building, the camel's nostrils and the Persian ice making? Well, the main element is a clever roof. And we want louvers to keep the sun off during the day. And then at night, we can open those louvers to make that radiative pathway to outer space clear. What that means is that the underside becomes slightly cooler. And then we can create these kind of fins based on camel's nostrils to create a lot of surface area for condensation. And we apply a particular mesh that's already been developed for dew collection. And in this part of the Middle East, it very often gets up to 100% humidity in the evening. So you've only got to drop the temperature by a few degrees C, and you can get moisture condensing, which would then drop down those fins into the little channels, and we can collect that and use it for something else. So in terms of the form of the building, we didn't really want the air close to the ground because that would be picking up too much heat from the ground. We needed the air from slightly further up the ground. That suggested some kind of wind scoop. We were also told that this might form the entrance to another part of the project. And so we were thinking about some kind of grand arch. And the combination of that wind scoop and the arch shape led us to this Pringle form. And our idea was to create this Pringle roof suspended above an outdoor amphitheater. And then the underside of this roof, this is the camel's nostril water collection surface. The water would run down to channels around this ring in the roof. And then when you're ready for the concert to start, you could have a kind of theatrical shower of rain around the stage that would tell people that it's time to be quiet and get ready for the concert to begin. This was a sketch of how it would look. So it's a concert amphitheater within an oasis garden. And that roof surface is capturing capturing water from the air to irrigate this oasis garden. And that's how it would look. We won that pitch, and then a few months later, the client decided not to build it, which is a shame, but never mind. Onwards and upwards. Final thing I'm going to talk about is a project that deals with regenerative landscapes. So on this project, we were trying to address a number of challenges simultaneously. So rather than looking at problems in isolation, like problems of desertification and climate change and species loss and so on, we thought maybe there's a way of tackling all those with clever integrated solutions. And the deserts, in many ways, they offer some of the solutions to our decarbonization crisis. You know, if we could capture just a small amount of the energy that falls on the world's deserts, that would go a long way to helping us shift away from fossil fuels. We were also quite struck that a lot of the world's deserts were actually vegetated quite a short time ago. When Julius Caesar arrived in North Africa, what he found was this wooded landscape of cedar trees and cypress trees. His armies cut all those trees down to make an intensive farm, and essentially that was a very extractive form of agriculture which completely changed the climate. Prior to that, it actually had quite plentiful rainfall and a lot of natural abundance. And on this project, the core technologies there were three core technologies. There are forms of solar energy, there's a type of greenhouse that is cooled and humidified with seawater, and there's desert revegetation technologies. And I think this idea, this is referred to as agrivoltaics. So it's the idea of using solar panels to create shade so that you can conduct agriculture underneath. I think it's very relevant to India and also to a lot of other hot parts of the world. And this can extend the growing season because it reduces the solar intensity on the crops. This was the first visualization we produced of what a really large-scale version would look like. And these three technologies have some very interesting synergies between them. They're actually much more productive together than they are separately. We managed to build a version of this in Qatar, This allowed us to test out all those 3 elements and a number of others. So we had 2 forms of solar energy. That's the seawater-cooled greenhouse in the middle. This area here, these are the desert revegetation experiments. We've got salt processing at the back, and then algae for biofuels over on the right-hand side. This was it on site. We managed to grow cucumbers throughout the summer months with half the amount of fresh water of conventional approaches. And this was opened by the Emir of Qatar during the climate change talks. And while we were kind of twiddling all the knobs, refining the technologies, we also monitored what was happening to the biodiversity. We had a hunch that this was going to be delivering some kind of regenerative benefits. At the start, there was basically nothing there. It was just a bare patch of desert. And we made a note of any mammals, birds, and insects that appeared on the site. So this little infographic shows what we achieved. Excuse me. So the first things to appear were flies. Nothing particularly interesting there. But then, literally the same day that we brought the first plants to site, we had the first birds appearing. And very soon after that, we had the first insects. Grasshoppers, crickets, and a month later, butterflies. And bear in mind, this was a long way from the nearest patch of planting, okay? Then, as the plants got more established, we had other types of birds, wagtails, we had more insects. Then we had a bit of a problem with rats, which was a pain, but we thought about contacting the World Health Organization, but they didn't return our calls. Then we also had mice to deal with, but still we were getting more birds and insects. 3 days after the algae ponds were filled, we had dragonflies appearing on the site. And again, I don't know where they came from. We were a long way from the nearest dragonfly habitat. But it seems that if you can create the right conditions for nature to recover, it has an amazing capacity to regenerate. So then a feral cat appeared, which is handy because the number of rats and mice went down. More birds, more insects. I'm going to have to speed up a bit. So that's a hoopoe, quite a rare bird. That's a rufous-tailed shrike, rock thrushes, wagtails, and eventually we had the first indigenous mammal. It's like a little hopping kangaroo that leaves very distinctive tracks. All that was achieved in just 8 months on a site 100 meters by 100 meters. And I'm convinced that if we were to do that on a bigger scale, over a longer time scale, that effect would be even more pronounced. I'm going to have to really skip through this. We also used ideas of ecosystem models to refine the synergies between the elements. And essentially what we were trying to do is to use what we had a lot of, sunlight, seawater, and carbon dioxide, to produce more of the things we need. And these are all the interconnections between the elements of the system. And sometimes when people look at that, they think, well, that looks hellishly complicated. How can you design for that? Well, it's getting easier because we designed an optimization tool that makes it much easier to connect together technologies in terms of their resource flows. Anything that is underutilized, that's a sign that you can add something to the system to create more value and steadily move towards a highly productive system that is close to zero waste and run entirely on solar energy. All right, now to draw together some conclusions. I've been talking about this idea of, in a way, humans taking on a kind of new role, of going well beyond just being a bit less bad into the realms of actually having a net positive impact. And if you doubt that that is possible, then just look at the difference that a single pair of beavers can make to a fire-ravaged landscape. We're an ingenious species, us humans. We ought to be capable of this. And if you doubt that we could do this at scale, well, look what was achieved in the lowest plateau in China. 30,000 square kilometers of barren land restored to biodiversity. And if this still sounds daunting, then I suggest you look at the prize that's on offer. We could be the first generation to witness the great return, the return of wildlife, the return of flora and fauna to our forests, the return of salmon runs to our rivers, the return of wildlife to the deserts, and a rewilding of the human spirit. All of that is within our reach if we take on a new role as co-enablers of the flourishing of all life for all time. Thank you.